regarding ionic bond, and I will try to continue the ionic bond. Okay. Now we have gone through the conditions for formation of ionic bond. We have characteristics of ionic bond we are discussing. Now we will discuss potential energy diagram for formation of ionic bond or electrovalent bond. Potential energy variation for formation of ionic bond or electrovalent bond. We will discuss now. Now, as we know that if we have charged particles Q1 and Q2 separated by distance of r, then force is given by 1 upon 4 pi E naught Q1 Q2 upon r square, and this expression is referred as Coulomb's law. This expression is referred as Coulomb's law. Now again, the potential energy of this system is 1 upon 4 pi E naught Q1 Q2 by R. This is expression for potential energy for these two charges. Now we will consider, for example, we have some ionic compound, ions. These are ions separated by infinite distance. Now these ions are tending to form ionic compound. These ions are tending to form ionic compound. These infinite ions, dot indicates what? Ions separated by infinite distance. Now they are forming ionic compound. Now we can have F net force equal to F attractive force between opposite charges, and simultaneously system also has F repulsive force between same charges. Now ions are coming close because F attractive is more than F repulsive. So these ions are moving close to each other. Okay, or we can write net potential energy of the system will be equal to potential energy due to attractive force plus potential energy due to repulsive force. So we have this. This is the potential energy due to attractive force and potential energy due to repulsive force. Okay. Now let me have, what is U net? Attractive force is between same charges. Okay. So what is U net? We have always positive. It will be always what? Negative. Attractive force is between opposite charges, either it is positive or negative. So product as per Coulomb's law will be always what? Negative. And repulsive forces is between same charges, so it is always positive. Okay. Now just see, what is attractive force? 1 upon 4 pi E naught Q1 Q2 by R, and it will be negative because one charge is positive and another charge is negative. Now again, repulsive force has expression something like this. Now it will be positive Q1 Q2 upon 4 pi E naught R raised power n. This is an expression where n is referred as Born exponent. So this quantity is always negative and this quantity is always positive, because positive negative results in attractive force, and positive positive is again positive, and negative negative is again negative. So we have this expression, or we can write if we have a system consists of cation, let's say we have a cation like AX, we have cation like AY plus, we have anion like BX minus, and these are forming compound AXBY. So what we can write this expression as minus 1 upon 4 pi E naught Q1. What is charge? What is charge on this? Bolo? Y times E. E is the charge on electron. What is charge on X? So we have what will X times E, and negative sign has been taken, and divided by distance R, plus 1 upon 4 pi E naught. Now same charges it will operate in between what below? Between same charges YY or XX. So what we have? We can have expression of what? 1 upon 4 pi Y into E, another is also Y into E upon R raised power n, plus 1 upon 4 pi E naught minus X into E minus X into E divided by R raised power n. We will have this. Something expression like this. So this quantity will be always negative and this quantity will be always positive. Now this will tend to form ionic compound, and the above equation U net is referred as Bond-Landy equation. Bond-Landy equation, referred as Bond-Landy equation. Now I will show the variation graphically. I will show the variation graphically. I'll just see it. Potential energy and R is interionic distance. Now we are going to plot the graph between potential energy and interionic distance. Now we always know that potential energy because of attractive force is always negative, and potential energy because of repulsive force is always positive. Okay, now just see it. This is the graph of potential energy due to attractive force. You just say it. It is always negative, and this is the graph of potential energy due to a repulsive force. It is always positive, and this is always negative. You just say. Now net of these two graphs is referred as, we know that as usual, U net is equal to U due to attractive force plus U due to repulsive force. This quantity is always negative and this quantity is always positive. The net of these two interaction is this is net graph. Now just see it. At infinite distance, when R is tending to infinity, U net is tending to 0, U attractive is tending to 0, and U repulsive is also tending to 0. But as these ions moves close, the potential energy keeps on decreasing because the contribution of attractive is more than, we know that mod of U attractive will be always greater than mod of U repulsive. So graph is like this, and this distance is the position of potential energy minimum, and this distance is referred as R0. This is called as actual ionic spacing or crystal spacing. This is the actual spacing in the ionic crystal. Okay, so this is the graph. This is the position of minimum potential. This point is very important. Now just see it. Before it, F attractive is more than F repulsive. At this point, F attractive is just equal to F repulsive, and after this we have F repulsive is greater than F attractive. So this is the position where potential energy is minimum. Now these ions will keep on moving till F attractive is equal to F repulsive. Till F attractive is greater than F repulsive, the system will, these ions will try to come closer and closer. And here is the position where ionic bond is formed. And at this position the potential energy is minimum. Or we can also write R0 must be equal to radius of cation plus radius of anion, because at this point these cations and anion will touch each other in the system. So this is the graph and how it comes. This explains the variation in potential energy of ionic crystals. So students, got the point? You just see it. Potential energy due to repulsive forces are always more than, and potential energy attractive, and this is always greater than, because both attractive and repulsive expression differs in the value of n, bond exponent. In case of attractive it is 1, in case of repulsive it is something more than 1. So this value is always, mod of this value is always greater than the value of this. So graph is keep on lying in between. Okay, so this explains your ionic bond, electrovalent bond, electrovalency, all these. Now next heading we have electrocatenic electrovalency of various atoms. Cationic electrovalency of various atoms. Now I'll just discuss. So we have discussed that cationic electrovalency is nothing but the charge on the cation. Anionic electrovalency is nothing but the charge on the anion. Now we will discuss the metal and their characteristic cationic electrovalency. Okay. Now just see it. Lithium, sodium, potassium, rubidium, cesium and francium. Beryllium, magnesium, calcium, strontium, barium and radium. Now just see it. These are called as alkali metals. And these are referred as alkaline earth metal. Alkali metal and alkaline earth metal. Now general configuration of this is inert gas NS1, inert gas NS2. This is the general configuration of this metal. Now they are electropositive. Now if alkali metals show loss of one electron, it will have a cation having inert gas configuration, and if alkaline earth metal forms shows loss of two electron, it will have inert gas configuration. And as usual, you know that inert gas systems or chemical units having inert gas configurations are relatively more stable. So alkali metal, where M is alkali metal, it will form M plus electron. So cationic electrovalency of alkali metal is +1. Okay. Now again, M is alkaline earth metal, alkaline earth metal. Now it will show loss of 2 electron, M2 plus, and gaining inert gas configuration. We have again inert gas. Here we have inert gas NS1, inert gas NS2. So we can write that permissible cationic electrovalency of lithium is +1, sodium +1, potassium +1, radium +1, cesium is +1, francium is +1, beryllium +2, magnesium +2, calcium +2, strontium +2, barium +2, and radium +2. Whenever these metals are present in any of the chemical unit, they will show this type of cationic electrovalency. They will try to form ionic bond. Okay, so permissible cationic electrovalency of alkali metal is +1 and that of alkaline earth metal is +2. And as a whole, these are referred as S block atoms. These are referred as block atoms. Now we'll discuss furthermore. Now we'll discuss P block. This is P block, boron family, we have carbon family, nitrogen family, oxygen family, and fluorine family. The general configuration: inert gas NS2NP1, NS2NP2, NS2NP3, NS2NP4, NS2NP5. Okay, so this is outermost electronic configuration. Now in case of P block element, there are some metalloids and metals, and metalloids and metals tend to form cation. So there are some. And in this case, first electron present in P subshells are lost, and then electron present in S subshell are lost simultaneously. Just listen. First electrons of P subshells are lost simultaneously, whatever be the number, and then electrons of S subshells are lost, whatever be the number, and generating various types of cationic. So what is permissible cationic electrovalency? +1 if loss of P, and both S are lost, is what will +3. So the characteristic cationic electrovalency of this boron family members is +1 and +3. Now carbon family member will show +2 and +4. Loss from P and loss from F, not in steps, direct. Okay, and I will explain later on why this is direct. +3 and +5, and rest does not forms any cationic electrovalency. And boron family includes boron, aluminium, gallium, indium, and thallium. Carbon, silicon, germanium, tin and lead, nitrogen, phosphorus, arsenic, antimony, and bismuth. So these are, out of these, cationic electrovalency is shown by aluminium onwards. Here it is shown by germanium onwards. Here it is shown by arsenic onwards. These does not form cation, this does not form cation, this does not form cation, this does not form. And these are, aluminium is metal, rest are metalloids. So lead will show two valencies, +2 and +4, and we used to attach a suffix s with low valency and ik with high valency. Let's say we have two ions Pb2 plus and Pb4 plus. We refer as plumbus, and we refer this as plumbic. Us with lower and ik with higher valency. Ik with higher valency. Similarly, we have aluminium ion +3 and +1. Aluminous, aluminic, and aluminic. You just write it. Similarly, we have Sn +2. Whenever some atom has Latin name, then we use Latin name. We call it stannous. Stannous, stannic. We don't refer it as tinous or tinnic. When some has Latin name, we use it Latin name. Similarly, we have arsenous, arsenic. Stevus, stevic. Bismuthus, bismuthic. So this is permissible cationic electrovalency of P block metals. Okay. So whenever we say that some lead is forming cation, so it will use this type of valency for formation of cation. Now we have permissible cationic electrovalency of D block atoms. Permissible cationic electrovalency of D block atom. Just remember, in case of D block atom, electrons are first lost from S subshell in steps, and then electrons are lost from D subshell in steps. But in case of P block, as we have gone through, as all P electrons are lost simultaneously, and then all S electrons are lost simultaneously. Now just see what happens here. Now scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So we have this. This is your first transition series. We have second transition series, then we have third transition series. Now general configuration is some of this is 3D1,4s2. Inert gas is common like argon in every case, and similar is in the case of other. This has 3D2,4s2, 3D3,4s2, 3D5,4s1, 3D5,4s2, 3D6,4s2, 3D7,4s2, 3D8,4s2, 3D10,4s1, 3D10,4s2. So we just say, now electrons are first lost from S and then they are lost from D in steps. Okay. So now what is permissible covalency of this group? First electron lost from, it is +2 and +3. Here we have +2, then we have +3 and +4, step loss. Now here we have +2, +3, +4, +5. These are permissible. Here we have +1, +2, +3, +4, +5 and +6. That's it. Here we have +2, +3, +4, +5, +6, +7. Just Mn. This is Mn group. This is chromium group. This is vanadium group. Now iron has only +2 and +3. This is for iron, but one such member is osmium. It shows +2, 2, +8. Osmium is the metal having highest cationic electrovalency. And why iron? Iron, because as you move here to here, size decreases. Now iron hesitate to go for further ionization because of decrease in size, and due to decrease in size, electrons are close to nucleus, they cannot be easily taken out. But in case of osmium, the distance of electron from nucleus is very far, and these 8 electrons can be withdrawn, generating cationic electrovalency of +8. This is the highest possible cationic electrovalency. Again, just for cobalt we have only +2 and +3. For nickel we have +2 and +3. For copper we have +1 and +2, and for zinc we have only +2. Cadmium also has +2, mercury also has +2. Silver has +1 and +3. Gold has +1 and +3. This is for nickel, this is for copper, this is for zinc. So these are the permissible. Now you can just bifurcate up to Mn. Whole of the ionization is possible, but after it there is a decrease in size, and it restricts the further ionization, with osmium having maximum possible cationic electrovalency. Okay. Now with low valency, in case of 2 valencies, we use again like in case of P block, we used to attach arsenic, like ferrous, ferric, cobaltus, cobaltic, nickelus, nickelic, cuprous, cupric, zinc, argentus, argentic, auras, auric. Whenever we have some Latin name, you have to use the word Latin name. Okay, and with variable valency we have to specify, like chromium 3, chromium 2, chromium 1, chromium 4, chromium 5, or chromium 6. Here we cannot use arsenic. Arsenic restriction is only possible, notation is only possible when we have only 2. If you don't want to use arsenic, you can also have iron 2 or iron 3, you just specify it. So this is the permissible cationic electrovalency of various D block atoms. And in the group it remains same. Here up to Mn group, everything is normal, but after iron starts, there is some change because of decrease in size. And simultaneously, mercury is the only metal which can form covalent bond like Hg++ and plus. We have 2 types of mercury, Hg. We call this as mercuric, and we generally don't use Latin name with mercury because of some, we can say it is convention, or spelling of hydrogarium is slightly tough. So with mercury we can use simple mercury. We don't try to use its Latin name because it is tough. And again we have per mercury we have one charge, we call it as mercurous, and it is the own mercurous ion, and it is the only metal which is existing in diatomic form. Rest of the metal and rest of the cations that we have seen are in monatomic state. This is the only metal which is forming covalent bond existing in diatomic. In short, we represent it as Hg2,2+, and we call as mercurous ion. So this is the permissible cationic electrovalency of D block. Okay. So these are the various cations that will found when we are dealing with ionic or electrovalent bond. Whenever these atoms are present, we have a tendency for formation of ionic bond, and these are the permissible valency and how it is to be used. Now I will discuss the anionic electrovalency of some of the anions, and as usual we know that anions are formed by non-metals. Okay, now I will just say permissible anionic electrovalency to valency. So anions are generally formed by non-metals because they are electronegative and they have tendency to gain electron. Now just say it, and most of the anions are present in p block. Now again we have boron family, we have carbon family, we have nitrogen family, we have oxygen family, we have halogens. With their general configuration, how many valence electron it has? 3 valence electron. It has 4 valence electron. It has 5 valence shell. It has 6 valence. It has 7 valence electrons. 7 valence electron. Now just say it. Now in case of boron we have 2s2 2p1. This is electronic configuration. Okay. Now boron tends to form a B3 minus ion. Okay. Having 6 electron, total electron 6, 3 its own outermost shell and 3 negative it gains. But just see, carbon is 4 electron outermost shell, it is 4 short with inert gas. So what electron it should take? 4 minus. Nitrogen has 5 electron, it is 3 short with inert gas. So what it should form? And 3 minus. Now it has inert gas. Oxygen is 2 short and fluorine is 1 short. And similar is in the case of their groups. And what we used to do, we used to name these anions as non-metal plus iodines. We call these anions as name of the anions. Name of anion is given by non-metal plus iod. So we called it this as boride ion. We call this as carbide ion. We call this as nitride ion. We call this as oxide ion, and we call this as fluoride ion. Non-metal plus iod. Now similarly we can have chloride ion, bromide ion and iodide ion. We can have sulfide ion, we can have selenide ion, we can have telluride ion, we can have phosphide ion, we can have arsenide ion, stibide ion, bismuthide ion. Okay, and we can further acetide ion. Now we can similarly we have Si4 minus siliconide ion and so on. So these are the various anions and their name. So what is acetide ion? At minus. What is telluride ion? T2 minus. And one more is TO2 minus, polonide ion in case of oxygen family. So these are the various characteristic anions. Okay. Now if someone says that write formula of aluminium phosphide, what does it mean? It is indicating the cation and anion. So what we say that what is aluminium phosphide? It is Al3 plus, what is phosphide ion? P3 minus. So formula is Alp. If someone says that just write aluminium oxide, what we said aluminium ion is Al3 plus oxide and O2 minus. So what just to do for maintaining charge balance we should have Al2O3, and it is convention that charges on the ions are not indicated, and this charge balance is to be carried out by simplest ratio of cation and anion. Okay. But someone says that write formula of barium fluoride, so we know that barium is alkaline earth metal, it should be BaF2. If someone says that write formula of calcium nitride, what we should write? Ca2 plus nitride is N3 minus, so we have Ca3, and so this is your calcium nitride. Okay, this is your aluminium oxide, this is your barium fluoride, this is calcium nitride. Okay. So we have this. Now this finishes your ionic bond or electrovalent bond. We have seen various characteristics. We have seen, so next chapter onwards we will discuss it regarding the covalent compound. Till that, goodbye.